Once in a while, you kind of like to know what we're doing. And this is our agenda for Wednesday, March 19. We've been doing different tests for infinite series to see if they were convergent or divergent. And our latest one was the integral test.
Was that muted?
No.
We can hear you now.
Yep, you're on fine.
Okay, thank you. It looks like we got our connection. But here's the agenda for today. We have some leftover problems, maybe from 11.2 that we haven't done. Then we went to 11.3, that's the integral test. Today we hope to move on to the comparison test, and that's in section 11.4. Okay, in the meantime, I think you need some even answers. I think I gave you all the even answers before at 11.2, but 11.3 had a few even answers too. So 11.3. Number 36 was even. And when I worked number 36, I said that n had to equal, well, actually it had to be greater than or equal to e to the 100, which is approximately 2.7 times 10 to the 43rd power. That's a lot of terms. I was kind of surprised on that one because they only wanted accuracy to the nearest hundredth, didn't they? Can you imagine taking the sum of that many terms? I bet you that would stall out the calculator for quite a few days. Trying to add up e to the 100th power, which is 2.7 times 10 to the 43rd. Imagine all those decimal places. But I believe that was the only even in 11.3. First we go back to 11.2 and see if we have to pick up anything there. Say number 54. Okay, now on 54 we get to use the computer algebra system, right? You say, see it says CAS. What's a computer algebra system? Calculator? Yeah, they said you can use your calculator as much as it's helpful.
Did you hand out?
Well, if I'm allowed to do that, I just started by typing it in the way it was and see if I could get an answer. But I wasn't too optimistic. I thought that'd be too easy, right, if I could just type it in? Well, if you look at it carefully, that's the kind we break into partial fractions. Can the calculator help to break into partial fractions? Yes, it can. So maybe that would help. So I broke it down into partial fractions and said, okay, calculator, now do it. Did it do it? No. So I found that the computer algebra system was pretty much worthless on that one, other than it helped me divide it into partial fractions, but I could have done that almost as fast by hand. Okay, we'll kind of go through what's involved and then show you what the human being has to do to finish it without the calculator, because you just can't make it simple enough for that thing. It just keeps refusing to find an answer. Okay? All right. We are doing problem 54 from 11.2. The original series started with n equals 2, went to infinity, and it was 1 over n cubed minus n. Okay, just to demonstrate what I was talking about a few minutes ago, it says you can use the computer algebra system on this one. Okay, there's our computer algebra system. Here's the computer algebra system magnified. I said, okay, if I'm going to use the computer algebra system, I'm just going to go to F3, grab number 4, and try it. 1 divided by the quantity n cubed plus n. Expand that, please. I even said please to this thing with respect to n. And you may start at 2, and you have to end at infinity, right? So I said, give me more of these kind, because I'm good at pushing buttons. I'm not good at thinking. And so I pushed the button, and there it was. Trouble is, I typed it in wrong, didn't I? That's not cheating fair. It was supposed to be n cubed minus n, not plus n, so now I'm sure it can do it. Yeah, it did a great job. Thank you, computer algebra system. I'm sure glad I spent all that big money on you. You are making my life simpler. But then the human being says, oh, don't despair. It just needs a little help, just needs a little nudge, right? And so we say, how did we do those kind by hand? Well, we split it into partial fractions. So I said, okay, we'll give it a second chance. We'll go to F2, and the expand command number 3, that's what we can use to get partial fractions. And I want it to expand 1 divided by the quantity n cubed minus n. I want it to expand that. And it did. Right? Okay, so I said, okay, computer algebra system, I've got it broken down for you. Why don't you just take that one and do it, and I'll forgive you. So I cleared the command line, and I went to F3 number 4. And then to save a little typing, I highlighted that partial fraction decomposition and pressed enter, and see it dumps it right in where I want it. And then it's ready to say comma n comma 2 comma infinity. And the computer algebra system says, sorry, I still can't do it. About that time you want to just kind of throw it against the wall. Or at least go back to Target and get your money back. So I did, and they said, well, I'm not going to give your money back because this was bought at Myers. I said, picky, picky. I said, I went to Target because it's closer to my house than Myers. And you won't take it back? I said, nope. They said, by the way, what's wrong with it? I said, well, it won't do what I want it to do. Well, what do you want it to do? I want it to sum an infinite series. Did you say infinite? Yeah. Well, get a life, they said. Everybody knows you can't sum an infinite number of things. What's the matter with you people? So I just kind of slunk out of there, hoping nobody noticed I was in there. Okay. So now what do? You abandon the machine because it can't do it. See, we did everything we could. We broke it into partial fractions, and it still. I even tried splitting it into 3 separate sums and then see if it could do it. I even went diamond enter, and that was impressive. See what it did? It changed it into decimal form, but it didn't do it. Frustrating, this machine. Sorry I ever bought it. Okay, out of my life. And now it's time for the human being to take over and start thinking. Okay, what I did learn from the computer algebra system is that This could be thought of as the sum of three different series. One of them was 1 over 2 times the quantity n minus 1. Another one was 1 over 2 times the quantity n plus 1. And the third one was n running from 2 to infinity of minus 1 over n. I did learn that from the calculator, okay? And I thought, well, maybe the human being could build on that. And guess what I was hoping might happen? If I wrote out some terms, I might see telescoping taking place. Remember that? Okay, in the first parentheses, we'll write out a bunch of terms for the first one, okay? We have to start with 2. Do you see why? Yeah, if you started with 1, I'd be dead in the water already, because I'd be division by 0, and then there's definitely no hope. In fact, I bet that wouldn't even converge at Kelvin. But definitely no hope for it, okay? But if you put in 2, what do you get? 1/2. And that's going to be plus. Put in 3. What do you get?
Quarter.
A quarter, right? I think. You know, 2 times n minus 1, 2 times 2 is 4. We can do that. All right, now let's put in a 3. Oh, wait a minute. 4, we're up to 4, because we started with 2. Put in 4. And put in 5. Want to make sure we got the pattern. What would the next one be? 1/10, and then 1/12, and on that one goes, right? That's the first one. Okay, we get to add that to the second one. What happens when you put 2 in that one? 1/6 plus, now put in 3. Now put in 4. So that's the second one, isn't it? All right, the third one I get to subtract, right? Because they're all negative. And that's just going to be 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6 plus 1/7, and so on, right? Do you see it telescope? No. I don't see telescoping. You know, usually we can see for every negative term there's a positive. Now here's the negative 1/2, and there's the plus 1/2, right? So, but here's a negative 1/3. I don't even have a negative 1 or a positive 1/3 anywhere. So now what do? Panic and wish you didn't assign it? Yeah. But I can't do that. I'm not allowed to. I got to think now. Think really hard. So I said, well, these are both positive, right? So let's make one series out of those 2. So we're going to take the first 2 and make 1 out of them. Well, 1/2 is unique, right? And the 1/4 is unique. But from there on, couldn't I take 1/6 plus 1/6 and put them together? What does that make? Yeah, 2/6 or 1/3. See, that's doing this one and that one. What's 1/8 plus 1/8? Quarter. What's 1/10 plus 1/10? What's happening? 1/12 plus 1/12. And then I still get to go minus 1/2, minus 1/3, minus 1/4, minus 1/5, minus 1/6, minus 1/7, and so on, right? So what I did is took the first 2 series and made 1 out of them. And now what's going to happen? This will cancel with that one. This will cancel with that one, this one with that one. Is there a pattern so it's going to continue canceling the rest of the way? What's the only thing that didn't get canceled?
Quarter.
I bet the answer is a quarter. Was that so bad? No, the only thing bad about this problem is that the stupid calculator got stumped. I mean, give me a break. This isn't that bad. Why can't the computer algebra system handle it? I don't know. Technology is a wonderful friend when it works. And that's why, unfortunately for you, we still emphasize understanding, ability to think, and stuff like that. Sorry about that. You probably lived too early. I bet your children won't have to think anymore. The machines will do everything. In other words, I'll take a machine like this. It'll have a little camera on it, a little eye, and I'll just sweep it over the problem. It'll absorb it, and then I'll go play video games, and when I'm done, it'll come back, and I'll look, and it'll say, here's your answer. I think that's what life's going to be in the future. But it hasn't arrived for you yet, so hang in there. It still demands that human beings think. Now, do you see why I kind of like that problem? I thought it was mean, personally, because it's misleading. It says use a computer algebra system, and it didn't work. Love it. Well, it did help me a little, right? At least it got the partial fractions for me. It saved me a little bit of work. Okay, do you have anything else left over from 11.2? Okay, how are you doing with the integral test? Do you like it? What a question. It works, but usually tends to be kind of a last resort, because it's not the quickest way to get there, but at least it gets you there. Are there any of those we should check out, explore more carefully? 11.3. Now, they're not all necessarily requiring integral test, but quite a few of them are. They deliberately chose series that need the integral test for lack of a better way to go. But that's not typically what I try first. And we'll gladly look at anything 11.3 if you need it. Which one? 21? Okay. This is number 21 in 11.3. The original series starts with n running from 2 to infinity, and it's 1 over n natural log of n. Okay, when I see natural log of n involved in a series, I know it's probably integral test. I might as well face it. I mean, it doesn't fit a p series with a log in there, and it doesn't fit a geometric series or anything that's simpler. But I have to first make a function of x that represents the terms of this series, and that would be 1 over x natural log of x. That's the function I have to integrate. But the integral test doesn't apply unless what three things are true? Positive, continuous, and decreasing. All right, the big issue with this is, what will I accept? I'm going to be pretty liberal. Don't just ignore these three conditions. And I'm not going to write down everything. I'm going to kind of do that verbally and mention what sorts of things you write down. How do you know it's positive? You just say, well, the numerator's 1. It's always positive. Okay? And if you start with n equal 2 and go from there, x is going to be positive, right? Because it's 2, 3, 4. And natural log of x is positive as long as x is bigger than 1, because the natural log of 1 is 0. That's all I want. Just a little argument. How do I know it's positive? Because the numerator is always positive. X is positive under the condition given, 2 to infinity. And natural log of x is positive as long as you're bigger than 1. And I'm going to be bigger than 1. I'm in. Okay, what about continuous? Well, the only way a fraction can be discontinuous is if the denominator is 0. So you just write a little argument, denominator can't be 0 because you're going from 2 to infinity. Okay, and natural log of 1 is 0. After that it stays positive. Just a little argument so I know you're thinking about it. What about decreasing? For decreasing, we typically like you just to take the derivative and show that it's negative, because if a derivative is negative, the function is decreasing. So it's denominator times derivative of numerator minus numerator times derivative of denominator. And I should have planned better. I need more room. Let me do that again. X natural log of x times 0 minus 1, because I need the product rule. And it'd be x times 1 over x plus natural log of x. And that'd be all over x natural log of x squared. Okay. One nice thing again about using the derivative is when there's quotient rule, don't you have something squared on the bottom? So you don't have to worry about him being negative, right? So it all depends on the numerator. Well, what do I have up there? I have minus 1 minus natural log of x, right? Isn't that all that's going to be up there? When you simplify it, I mean, this is 0. And that's all over x natural log of x squared. And then you just make the argument, denominator is always positive for x greater than or equal to 2. And the numerator is always negative. See those negative signs? As long as natural log of x is positive, you have a negative number. Negative divided by positive is a negative, so it's decreasing always. That's it. Okay, for the conditions and what I'm looking for, about the only way to lose points on the conditions is 2 ways. Ignore them, pretend they don't exist, you'll get docked for that. Or basically say, clearly these are all true. That's not quite good enough either. You got to have a little more than that. Just explain how you know, okay? But I don't want you to be frightened about that part of it or worry. As long as you show that you know they belong and you can explain briefly how you know, I'll let it go. Okay, what's the heart of the test then? The fact that this series, its convergence or divergence depends on this integral. Okay, I've got to check this integral. The convergence or divergence is right along with this integral. Okay, here I'm pretty fussy. Don't leave pieces out. Make sure you write this is the limit as t approaches infinity of the integral from 2 to t of 1 over x times natural log of x dx. Now, how do you integrate this? We've done this one before, and we did it by straight substitution. What did we let u equal when we had this integral in chapter 7? Yes, we let it be natural log of x. Then the du would be, yeah, I'm not doing parts, I don't need that much. It doesn't have to be that heavy. Which means that dx gets replaced with what? X times du. Okay, but if x equals 2, right there, then what does u become? Remember how we have to change our limits? Yeah, natural log of 2. Just look right here. And if x equals t, what does u become? Yep, natural log of t. So this integral becomes the limit as t approaches infinity of the integral from natural log of 2 to natural log of t. And now let's do our substitution. Well, we have 1 over x times u, because u was natural log of x, and what it was dx? It was x du. Is that a good sign? Yeah, we wanted the x's to disappear. So this now becomes the limit as t approaches infinity of the integral from natural log of 2 to the natural log of t of just 1 over u du. Okay, is that something we can integrate? It is. So this becomes the limit as t approaches infinity of, what's the antiderivative of 1 over u? Okay, and that still has to be evaluated from natural log of 2 to natural log of t, right? Which becomes the limit as t approaches infinity of the natural log of what? Oh, first I replace u with the natural log of t. Then I go minus the natural log of the natural log of 2. And now I have to analyze what's going to happen if t goes to infinity. Well, as t goes to infinity, what happens to the natural log of t? Well, if you recall the graph of just natural log, it's like this, isn't it? So what's happening to natural log as t goes to infinity? Well, natural log of t is going to go to infinity, which means you have to take natural log of something going to infinity again. I think this is infinity. Minus the natural log of the natural log of 2. Well, if you have infinity in your answer, what happens to that integral? Diverges, yeah. To converge, it has to equal some nice real number. So we say, therefore, the integral from 2 to infinity of 1 over x natural log of x dx diverges. And the series n running from 2 to infinity of 1 over n natural log of n also diverges, and that's by the integral test. Does that answer your question? Did Bob get it to diverge too? Yeah. You see now why integral test is not the one we rush in to do first? I mean, it's involved, isn't it? And you never know just how well the integral is going to go either. In this case, it's substitution. So, needless to say, probably, on the test eventually, if we ever get that far, guess how many times you have to use the integral test? Do people ever use it more than once? Yeah, because there's 2 sections on the test. One section, I tell you what test you have to use. And one problem will say, you must use the integral test on this problem. I'm not going to make it too bad, you know. I mean, the integration should go fairly smoothly, but after that, there'll be a section that says, pick any test that you think is going to work smoothly for you. And some people actually use the integral test in that section, and it works, and they get full credit, but they just worked a little harder than they had to. But if you can't think of anything else and this works, it's better than leaving it blank, right? But the odds are when you have a choice of tests, you probably won't have to use this one. There'll probably be something else that works if you can see it. Okay, was there anything else from 11.3? Any other type of problem that just kind of eluded you a little bit?
Can you do 36?
36, okay. 36 is trying to find how many terms of the series you would need to add to get within 1/100th of the actual sum. Now the implication here was the series must be what kind? I mean, or they couldn't even ask the question. It must be convergent or they couldn't even ask for a sum, right? An approximation. Yes, you may assume that. You don't have to go through all the work and prove it converges. Okay? You may assume, since they asked the question, approximate the sum. I suppose the answer could be there is none because it diverges. But we are going to assume, since they asked for a sum, they must already know it converges. Okay, so we are going to use the fact that if, I better write the problem down. This is number 36 in 13.3. Okay, if f of x, which is equal to 1 over x times natural log of x squared, is positive, continuous, and decreasing, okay, has the same conditions as the integral test, then we guarantee that the error, if you sum up n terms, we call that r sub n, is less than or equal to some integral. What integral? The one that runs from n to infinity. N is whatever this is, of 1 over x natural log of x squared dx. Okay, we're guaranteed that the error, represented by r sub n, it means the error after you add up n terms of the series, is guaranteed to be less than or equal to the value of that integral. So we say if we make the value of that integral less than or equal to 0.01, then won't the error automatically be less than or equal to that too? Error is guaranteed to be less than or equal to this value of the integral. So if I pick n so that the value of the integral is less than or equal to that, then my error will be less than or equal to that too. Okay, what's the first thing you're supposed to do? Make sure it's positive, continuous, decreasing. Well, here's the function. Is it always positive? Well, the original series started at 2. 2 to infinity of 1 over n natural log of n squared. So yeah, it's definitely positive. It's the same sort of argument we just did. It's a very similar problem. Is it continuous? Yeah, it's only discontinuous if the denominator is 0. It can't be if n is 2. Okay, just got to say that. Is it always decreasing? Well, I could take the derivative and show you, just like last time, it stays negative. So therefore, it's always decreasing. Okay, assuming we've done all that, we have to work with this. So what we must do is solve the integral from n to infinity of 1 over x natural log of x squared dx less than or equal to 0.01. We have to solve that for n. I want to find what value of n is going to make that true. Okay, but the problem is it's an improper integral. So that means I have to solve the limit as t approaches infinity of the integral from n to t of 1 over x times natural log of x, the quantity squared dx, less than or equal to 0.01. I have to solve that. Okay, next comes integrate it. Well, to integrate it, I let u equal natural log of x, kind of like the last one we did. And then the du is going to be 1 over x dx, which means the dx is going to be x times du. And then changing my limits, if x equals n, what is u? Right, natural log of n. If x equals t, what is u? Natural log of t. So this now becomes the limit as t approaches infinity of the integral from natural log of n to natural log of t. And then I can do my substitution and I get 1 over x times u squared, right? And then the dx was x du. And again, they'll just cancel. But that still has to be less than or equal to 0.01. Remember, we're still solving an inequality here. Should put implies there. Implies the limit as t approaches infinity. Okay, what's the antiderivative of u squared? Think of it as u to the minus 2. Minus u to the minus 1. That's it. That has to go from natural log of n to the natural log of t. Still less than or equal to 0.01. I think I would rewrite that as the limit as t goes to infinity of minus 1 over u, going from natural log of n to natural log of t. Okay, so the limit as t goes to infinity. What happens if you put the upper limit in there? You get minus 1 over natural log of t, right? What if you put the lower limit in there? Well, you get plus 1 over natural log of n. And that has to be less than or equal to 0.01. Okay, as t goes to infinity, what's going to happen to this? It's going to go to 0 because the numerator stays constant. Denominator becomes infinitely large. So you end up with 1 over the natural log of n is less than or equal to 0.01. And then you got to solve that for n. To solve that for n, we can say 1 is less than or equal to 0.01 times natural log of n. That means natural log of n is greater than or equal to 100. Multiply each side by 100. Get rid of the decimal. Which means n is greater than or equal to e to the 100th power. Remember how to convert logs to exponents? E to the 100th less than or equal to n. And there's how I got my answer. I found that almost unbelievable because that's such a huge number of terms. I only wanted to get within the nearest 100th, right? But some series are like that. They converge so slowly. It takes forever. I mean, that number is probably bigger than the national debt, so we know it's huge. I don't worry about the national debt. You know why? Because I'm so old, it's going to be your problem. Thanks a lot, right? Hey, what can I say? I'm not the one that voted in all those spending programs. I did my best to fight them, but they didn't listen to me. I said, the national debt is growing exponentially. And I said, oh, you math people. You talk in riddles. Okay, you'll see. I do feel sorry for you, though. I don't know what's going to happen. You can start to see it a little bit already, you know, with the market. It's so, you know, we got that much debt, the dollar value goes down, and then the debt gets worse, and then people get nervous, and the market tends to, bad news. So maybe we shouldn't put too much stock in this life, maybe. Maybe that's the point. Okay, do you have any other questions?
41.
Who?
41.
41? That one was bad? I didn't get that far. I said nobody's going to ask me to do 41, so I went to bed instead. How did you know I didn't do 41? You trying to make me look bad? Yeah? At least he's honest. I used to be like that as a student too. I'd try to look for problems that were really bad and always ask the teacher to do that and then sit back and enjoy while they were sweating. Somebody said to me, "Don't you feel a little bit bad about that, being so mean?" I said, "Nah, I'll never be a teacher. Put these guys on the hot spot. It's good for them." Right? So here I am. Thanks for returning the favor. Will you help me if I run stuck? He says no. Good grief. Hey, remember, I still have to give you guys grades. I have a little power yet. Now you're going to help me?
I'll think about it.
He'll think about it. See, I know what to do to make people think anyway. Okay, in the meantime, I was doing all that peripheral stuff while I was madly thinking about how I was going to survive this problem. But you know my strategy, right? 41, section 11.3. Write the name of the problem slowly. Think desperately fast. What is it? It's a series where n runs from 1 to infinity of b to the natural log of n, and it says find positive values of b for which the series is convergent. So I guess they're saying if you pick b to be the right kind of positive number, you can actually get a series that converges, but if you don't pick it right, it'll diverge. Oh man. Well, when I see a power like that, it kind of reminds me of a geometric series, but that would be b to the nth. You know, if they said b to the nth, it'd really be easy. Because then b would have to be between 0 and 1, I mean minus 1 and 1, but if it's positive, it'd have to be between 0 and 1. So if I had just b to the nth, that would be a gift, wouldn't it? I think I'll put that one on the test. Make it b to the nth instead of natural log of n, and then say, tell me for what values of b this will converge. Because then it would be geometric if it was b to the nth. But the natural log of n screwed that up. So what does he do when he doesn't know how to do the problem? He makes up problems similar to it that he can do. Hey, I was one of the top students in Education 101. How to get by when you don't know what you're doing, and try not let the students let on or know that you don't know what you're doing. That was one of the most valuable parts of that course. If you don't know what you're doing, how can you fool your students? Well, I'm using trick number 1. Just talk about stuff that is sort of related to the problem. Talk about a problem you can do, and talk about how you wish it were that one instead. But eventually you got to get right down to it and say, this isn't the problem you wished it were. How do you do this one? You know what I'm thinking right now? I bet we could make that into a p-series. He said, no, you can't make it into a p-series because a p-series is like 1 over n has to be the base, and then p is the exponent, right? But I'm thinking with logs, I might be able to pull that off. Make it into a p series, and then p has to be greater than 1 to converge. What do you think? I think it's worth pursuing. So, can I take b to the natural log of n and turn it into 1 over n to the p? Well, let me see. This is what I'm thinking. Recall that b can be written in terms of logs. B can be written as e to what power? Do you remember that property of logs? E to the natural log of b is equal to b. Therefore, b to the natural log of n could be thought of as e to the natural log of b, all raised to the natural log of n. And about this time, the students start enjoying it because they say, he's getting himself into a real mess here. Well, if it gets messy enough, maybe I can just fake it and say, you know, if nobody knows what you're doing, that's tactic number 2, Ed 101. Get the problem so messy looking that nobody knows what you're doing, then you can get by with anything after that. Hey, that means b to the natural log of n could be written as e to the natural log of n raised to the natural log of b. Is he playing games here? Is that really true? Are these two the same? Well, what do you do to the exponents when one's inside the parentheses and one's outside? You multiply them, right? Is multiplication commutative? So could I switch it to this? Now you remember, deep down I told you I had a goal. I wanted to get n to a power, right? What can I change e to the natural log of n into? N. I did it. I took that problem and I got it so it's a power of n, right? Okay, now I think it's going to be kind of easy after that. So I tried to turn it into a p series by getting n to a power. Therefore, the series n running from 1 to infinity of b to the natural log of n is the same as doing the series n running from 1 to infinity of n to the natural log of b. They're the same series. But that could be written as n running from 1 to infinity of 1 over n to what power? Negative natural log of b, right? This is a p series with p equal to what? Negative natural log of b. By the way, Bertel, you're helping me.
Oh, am I?
Yeah.
That's not.
Well, that's up to you. I mean, I really appreciate it, but you said you weren't sure if you were going to, and I just wanted you to know you're helping me. So if your goal was not to help me, you know, I just thought it was only fair to tell you, yes, you're helping me. You gave me all kinds of answers. Now, I appreciate it, but you said you weren't going to do it.
I said I'll think about it.
You thought about it and said maybe it's best to keep him in a good mood before he writes a test someday? Good thinking. Good thinking. Okay. What does P have to be for a P series like that to converge? Greater than 1. Therefore, to converge, P has to be bigger than 1, which implies minus natural log of B has to be greater than 1. Well, multiply each side by minus 1, and the natural log of B has to be what? Remember, when you multiply by negative 1, you have to switch the order, right? And that means B has to be less than E to what power? In other words, B has to be less than 1 over E. Is that what Bob got or not? I obviously didn't look at his answer if I didn't work the problem. I think it's got to be right. I don't see any big mistakes there, do you? So B has to be less than 1 over E. As long as B is less than 1 over E, it should be okay. Of course, it has to be positive, so it means it has to be greater than 0 too. I guess that goes without saying. So somewhere B has to be somewhere between 0 and 1 over E. Nice problem. I'm glad I assigned it now. Does it make sense? So what was the strategy? Turn it into a p-series. And that's typically what we try to do on something like that. Either make it into a geometric or make it into a p-series where the testing is easy. Okay? And then the work here was trying to make it look like a p-series. Once I got it looking like a p-series, the finish was pretty straight. Okay, have we done enough, or is there more from that section we have to check? Well, let me move on to the next test, and I promise on Monday I'll come back to here and say, is there anything that came up over the weekend in 11.3 that you might want to explore further? What happened to Friday? No school. Why? Well, this being a totally politically correct college, you would check the schedule and it says what? Holiday. Holiday. Spring holiday. Of course, deep down we all know why we're having off on Friday, don't we? But don't you dare say it. What if I said it on national TV why we're really having off on Friday? I'd probably get hauled in and disciplined. So, on national TV, we're having off on Friday because it's Good Friday. Go ahead, go after me, see if I care. The administration doesn't like it when I do that. You know, come on, keep it clean. Hey, why can't I tell the truth? We wouldn't have that off if it wasn't Good Friday, would we? So I don't care, call it whatever you want. And I'm not offended by the fact that on Good Friday, we're going to give people a chance to have this day special if they want it to be. Right? I don't have a problem with that. But then, I'm not sensitive enough. So, anyway, no class on Friday, so that's why I said on Monday, we'll come back to this section and see if anything came up. You might have a different teacher, but I'll make sure I send him the note that I promised to go back, so hopefully the new teacher will too. Okay? So we're headed for 11.4, a new test. It's called the comparison test. Okay. The people here need this handout, so give me a chance to pass that out. Oh, the comparison test. How does the comparison test compare to the integral test? It's easier to do. I told you the tests are going to get easier as we go, not harder. We got the hard one out of the way first. The integral test. And now after this, it gets a little easier to apply.
That's it. George.
Okay, here it is. Purpose. The purpose is to determine convergence or divergence by comparing the series you know nothing about to another series that is known to be either convergent or divergent. That's the purpose. We want to compare a given series, which we have no idea what it does, and say, instead of looking at that one, let's just compare it to another series where we know what's happening. Sort of makes sense. Well, how does the principle work here? Well, we're going to give the principle by way of an example first before we convert it to a theorem. But here's a series that we know a lot about. If I said, what does this series do? You'd kind of look at it and say, boy, that thing looks a lot like what kind? Geometric. Can you see the common ratio is a third? Every time you go to the next term, you're multiplying by a third. So you say that's a geometric, and thus is known to converge because the ratio equals 1/3, which is between -1 and 1. And we know from our work with geometric series, if the ratio is between 1 and -1, that constant ratio between consecutive terms, it converges, right? Okay, now here's a series I know nothing about. And we'll try to keep them both on the screen here. You see this one down here? He's not geometric, he's not a p-series. He's nothing that's well known. But when I look at this series and look at the first series, they have similarities, don't they? But the thing that you have to note is if you compare them term by term, compare the first term, okay? And my new series, the first term is smaller than the first term of the original. What about the second term? Smaller than the second term of the original. Third term, smaller than the third here. Smaller than the fourth. Smaller all the way. So you know what the theory is? This series up here, the well-known one, definitely converges, right? Now, if these terms are smaller than the terms in that one, now remember, convergence means it has a what? Sum, right? Now, if this has a sum, and these terms stay consistently smaller than the terms here, then shouldn't it have a sum as well? You see the reasoning here? Now, that only is going to work if the terms stay positive. I mean, I could make these terms negative, you know, like -1 plus -2 plus -3 plus -4, and they stay smaller too, don't they? But -1 plus -2 plus -3 plus -4, that's not going to converge. There's no hope for that sum. But as long as you keep the terms positive, and the terms are less than the terms in a series that's known to converge, this one's got to converge too. That's how the comparison test works. Guess what the biggest issue is? Well, you see, in an actual problem, you're going to have a series like that, and you have to come up with one that it compares to, that you know something about. That's where the fun is. But it's not as bad as it seems. Okay, the terms of this series are term by term smaller or less than. They're smaller or less than the known convergent geometric series. So even though the sum of this series is unknown, at least we know that it must converge. And we already pointed out to you, knowing that it converges is a great thing, because even if we don't know the exact sum, we can at least approximate it, right? By adding up 10 terms or 20 or whatever. But you can't approximate a sum that doesn't exist. And knowing it converges says the sum does exist. So if I added up 20 terms, I'd have an approximation for the sum. Okay, it works the other way too. Another example, a series like 7 plus 7 halves plus 7 thirds plus 7 fourths and so on is term by term greater than the terms in the known divergent harmonic series. Yeah, this is a P series where P is 1. This is 1 over n to the P, where n P is 1 over n to the first, right? 1 plus 1 half plus 1 third. And if P is less than or equal to 1, it diverges. But we gave this one a special name. We called it the harmonic series. But can you see 7 is bigger than 1, 7 halves is bigger than 1 half, 7 thirds is bigger than 1 third, and so on? Now, this series has no sum, right? It's divergent. Now, is it possible that a sum that's bigger than a divergent series could possibly have a sum? You see, if your series is bigger than a known divergent series, then yours can't converge. It's got to have a sum that's bigger than this one. But this one doesn't have a sum, it's so huge. So that one can't either. So it says the given series that we're wondering about must also diverge. Now what we hope you got out of these examples was this principle. If a series is to converge, it has to be smaller than a known convergent series. And if a series is to diverge, it's got to be bigger than a known divergent series. Does that seem right to you in your mind? Because if it doesn't, you're going to mix it up. One more time. For a series to converge, it has to be smaller than a known convergent series. For a series to diverge, it has to be bigger than a known divergent series. Okay, that's all summarized in the infamous comparison test right here. It says, if you have a series, n running from 1 to infinity of a sub n, and you have another series, n running from 1 to infinity of b sub n, and these are both series with positive terms, that's basically the only condition. Make sure that both of your series have positive terms. Then, if the second series is known to converge, and the terms of my a sub n series stay less than or equal to the terms of the b sub n series, then what can I say? The series n running from 1 to infinity of a sub n must also converge. Okay, what if the b sub n series diverges and the terms of the a sub n series stay greater than or equal to the terms of the b sub n series? Well, then we will guarantee that the series n running from 1 to infinity of a sub n also diverges. Also diverges. Okay, and then just to help us along our way a little bit, what are some well-known series that are recommended to use for comparisons to lesser-known series? Well, one is obviously the P series. We know a lot about him. And the P series is n running from 1 to infinity of 1 over n to the P. That's a good series to use for comparison because we know that it converges if P is what? Greater than 1, but it diverges if P is less than or equal to 1. So when you pick a series to compare to, you want to pick one you know something about. That's kind of the point. And here's some that we know something about. There's another one we haven't run into before. It's called the factorial series. We kind of save it for this point because it's often used for convergence comparison purposes. But it looks like this. N running from 1 to infinity of 1 over n factorial. And the factorial series always converges. So you pick any integer n, and you do factorial, it always converges. We'll be able to prove that later, but for now it's a handy one to use. The other one, of course, you already know about is the geometric series. They're good to use for comparison because we know a lot about them. What do geometric series look like in summation notation? They have some value, some number to the nth power. That's how you recognize the geometric series in summation notation. It has a number to a power n. Now the n doesn't have to be plain n. It can be n minus 1, n plus 7, just so there's an n up here. Well, this converges if r is between what two numbers? Okay. But it diverges if r is greater than or equal to 1 or if r is less than or equal to minus 1. Okay. Let's do a problem so we can see exactly how that works. As I've mentioned before, the biggest issue is trying to come up with a series to compare it to. Well, to help you see what might be used on this one, I'm going to rewrite the series as 1 over n to the 1/2 and then minus 1. Now, why did I do that? Because now I see n to a power. And when you have n to a power involved in the series, then probably compare to what kind? P series have n to a power, right? So I'm going to compare to the series n equals 1 to infinity of just plain 1 over n to the 1/2.
Doesn't it have to start at 2?
Pardon me?
Doesn't it have to start at 2?
Oh, does it start at 2? It better. Thank you. Yeah, that's a typo. If this doesn't start at 2, there's no hope for it, is there? Thank you. I even wrote that in my notes. I should read them more often. It says, make sure you point out to the students that there's an error here. It should be n equals 2. You say, I don't believe that. You're just faking it. Okay, I'll show you my original notes. What do you see? I didn't just write that either. There, take that. I was telling the truth for once. Okay? Now that I fixed it, there's at least hope for this thing. So I'm going to compare it to 1 over n to the 1/2, which is a known, what kind of series? Convergent or divergent? Okay, it's a known divergent P series with P equal to 1/2, which is less than 1, right? Okay? All right. Now, what do I have to establish? Two things. First thing I have to verify is, do the series have positive terms? That's the first question I have to check. That's both of them. And the answer is yes. You can put yes factorial for emphasis if you want. Yes, and then you should give a quick reason how you know. Because if n is greater than or equal to 2, n to the 1/2 is greater than 0, and n to the 1/2 minus 1 is also greater than 0. And we assume that the reader could say n to the 1/2 starting with 2 is the square root of 2, square root of 3, square root of 4, square root of 5. And right here is the issue. The square root of 2 is about 1.414, and if you subtract 1 it's still positive. But you got to show to me that yes, you thought about it and this is how you know, okay? All right, the big thing is right here. This is the one we have to focus on. The question is 1 over n to the 1/2 minus 1, because that's the nth term of your series, does that stay greater than or equal to 1 over n to the 1/2? That's the other question you have to answer. Now, why do I have to have this term greater than or equal to that? Because I'm comparing it to what kind of a series? A divergent one? And if you want to compare it to a divergent series, you got to make sure your terms are bigger than that one, otherwise it's no good. Now, if I was comparing to a convergent series, I'd want these terms to be less than or equal to that. Okay? All right. Now, how do you make that argument? Well, I want to introduce you to something that's not in many books anymore, but it's such a valuable tool. I probably use this tool more in grad school than anyone else. And yet, it doesn't seem to be taught. It's called an indirect proof or verification, if that's what you want to call it. And I want to show you how that works, because I think that's a tool you ought to have in your kit somewhere. Now, I guess if you looked at Bob's answer, he'd do some hand waving and some nebulous argument that's not very concrete, till finally his verbiage is so great you say, okay, whatever you say. You know, that happens sometimes, right? People don't have a good argument, so they just talk more and more and more till you get so sick of them talking, you just say whatever. That's kind of the way Bob's arguments are. This can be clean and precise if you're willing to do an indirect verification. Okay. An indirect verification, you start by supposing the exact opposite of what you want. So you say, I want this to be greater than or equal to that. Well, let's just suppose for now that 1 over n to the 1/2 minus 1 was actually less than 1 over n to the 1/2. Now, we want this statement to be what? False. Right? I want to show this is false. So I just suppose that we're true for a minute. What should happen if it's truly false? It should lead to a glaring contradiction of some sort. You know, time you start with a false premise, if you reason from there, shouldn't you eventually get into a real bind, a contradiction? Well, the contradiction is going to be very clean, because the next step, if this is true, if you suppose that's true, then what else do you have to accept? The fact that n to the 1/2 is less than n to the 1/2 minus 1. Can you see how this follows from that? Do you know what I did? What did I do? Well, sort of, but you're not supposed to cross multiply with inequality. But it does work if everything's what? Positive. And we know you can't even do this problem unless the terms are positive. You see, technically what I did is I multiplied each side by the common denominator. In other words, I multiplied each side by this, n to the 1/2 times n to the 1/2 minus 1. I multiplied that on each side. And then it cancels here and I'm left with n to the 1/2, and then there it cancels the n to the 1/2 and I'm left with that. But whatever. It's true. Okay, what can I do next? You know, if you suppose this, then you got to buy this too. But if you buy this one, you can subtract n to the 1/2 from each side, right? What happens when you do that? Isn't that a glaring contradiction? I like indirect proof because it's very concrete, and if you keep going, you get some kind of a glaring contradiction. And as soon as that hits, what we used to do is, that's the logical symbol for contradiction, two arrows meeting head on. Did you know that? That's the symbol for contradiction. As soon as you hit it, you say contradiction. Okay, what caused this contradiction? A bad supposition, right? So anything that leads to contradiction must have been false. So you finish it by saying, therefore, the supposition is false, and that's clearly written right up there. And what does that make automatically true then? The opposite. But what's the opposite of this? What I wanted originally, see? Have you ever been taught that kind of proof? Do they still do it? I mean, they used to teach this kind of proof in high school, but I don't know if they do it anymore. You probably haven't seen it. But trust me, it's a handy tool. It's a lot cleaner and more precise and easier to follow, I think, than a hand waving trying to convince people that it's really less or greater than or equal. Okay, don't forget, after all that excitement, what you were trying to do. Don't forget to answer the question. What was the question? The question was, what does this series do? Well, what have I just shown? I've shown that it satisfies the conditions of the comparison test. And I was comparing it to what kind of a series? Okay, therefore, by the comparison test, the series n running from 1 to infinity of 1 over the square root of n minus 1 must also diverge. And that's the final conclusion. How you know? You showed that you satisfy the comparison test. You compared to a divergent series, so mine must diverge as well. I think it's much less work than the integral test, but I don't know, you can judge for yourself. Okay, there is another part to this, however, and that's called the limit comparison test. As we pointed out, occasionally it's difficult to establish whether or not a sub n is less than or equal to b sub n, or maybe a sub n is greater than or equal to b sub n for all n. Now the last one, we used a little indirect proof and reached a glaring contradiction fairly soon, so that worked smoothly, but sometimes it's really hard to verify which one is really true. Then the limit comparison test can sometimes be used as an alternative. Okay, what does the limit comparison test say? It says suppose that a sub n is one series, b sub n is another series, and they both have what? Positive terms. That's the condition for all comparison tests. Okay, it says if you take the limit of the nth term of the first series divided by the limit of the nth term of the second series, and you get a number that's bigger than 0, then the series a sub n and the series b sub n both converge or diverge together. So if the limit of the ratio of their nth terms turns out to be a number that's greater than 0, then whatever one series does, the other one does. Now, of course, we're assuming that you know what one of them does, right? You picked it that way. So this way you don't have to go through all the work of trying to show that a sub n is less than or equal to b sub n, or vice versa. Just take the limit of their nth terms, and if it turns out to be positive, they do the same thing. Whatever one does, the other one does. Okay, what if that limit turned out to be 0? Then if the series, whose term is on the bottom here, converges, then the a sub n series also converges. Well, what if that limit turns out to be infinity? Well, then if the series whose nth term is on the bottom diverges, then we will guarantee that the series a sub n also diverges. Okay, so there's 3 things that can happen. The limit turns out to be just some positive number, then whatever one does, the other does. If it turns out to be 0, then if one converges, the other one will too. If it turns out to be infinity, then if one diverges, the other one will. What if the limit turns out to be negative? It can't. You know why? Because both of these terms have to be positive, see? So the worst that could happen is the limit is 0. It could be a positive number, or it could be infinity. Okay, we've covered the 3 possibilities. Okay, we're going to try it on this one. We're going to test this series for convergence or divergence. Okay, but first we need a comparison series. What do you think we should pick? Well, I want to pick one that I know something about. What kind of a series tends to have numbers to the nth power? Now, last time it was n to a power. That was p series. Now it's reversed. Now it's a number to the nth. What kind of series tend to be that kind? Okay, so what am I going to do? Compare it to a geometric series. And can you see which one we're probably going to use? You get used to it, and it's not so bad to pick them out. And that's the same as the series n running from 1 to infinity of 2/3 to the nth. Okay, what kind of a series did I just construct there? Okay, this is a geometric series which is known for what? Converge. Why? Because 2/3 is greater than -1 but less than 1. Because 2/3 is between 1 and -1. Okay. Now, instead of trying to prove that the terms of my series stay smaller than the terms in the given series, I'm going to use the limit comparison test. But before you do, what are you supposed to establish? The terms stay. So you're supposed to make an argument. Terms of both series are always positive because exponential functions of the form a to the x are never negative. That's how I know they stay positive. In other words, if you would graph a to the x, it's one of these things. Okay, it never gets below the x-axis. So if anything of the form a to the x is always positive, what do I have? I have 2 to the n which stays positive. I have 3 to the n that stays positive, so the quotient is. If I take 2 to the nth which is positive, add 1. Take 3 to the nth which is always positive, add 1. Just some reference here. I mean, don't ignore the fact that they have to be positive. Say something here. Okay, how do you know that the terms stay positive? Okay, now I'm going to check the limit as n goes to infinity of a sub n divided by b sub n. Now when you do this limit, you have to know what to put where. Which one do you always put on top? The unknown one, that one. And which one is always on the bottom? The known one. So what I have to do is take the limit as n goes to infinity of 1 plus 2 to the nth divided by 1 plus 3 to the nth all over 2 to the nth divided by 3 to the nth. The parentheses are just for emphasis on how this fraction is divided. Okay, I want to take that limit and see what happens. Okay, this is the same as the limit as n approaches infinity of 1 plus 2 to the nth over 1 plus 3 to the nth times what?
3 to that.
Yeah, 3 to the nth over 2 to the nth. Invert and multiply. Okay, let's distribute. What's 3 to the nth times 1? Okay, be careful. What's 3 to the nth times 2 to the nth? Like that. What is that? 3 to the nth times 2 to the nth. This is just my scratch paper. Isn't that the same as 3 times 2 all to the nth? Isn't that a property of exponents? Remember that one from algebra? Because you apply the n to both pieces, but what is that equal to? It used to be, I would just put plus 6 to the nth and I'd get some protest. And they said, you're not doing your algebra right. Actually, I am. Maybe it doesn't feel quite right, but 2 to the nth times 3 to the nth is actually 6 to the nth. Here's the steps I'm thinking here. Okay, then likewise on the bottom you get 2 to the nth plus what? 6 to the nth. Okay, that is equal to infinity over infinity, which means I can apply what? The problem is I tried doing L'Hopital's rule and I got nowhere. I applied L'Hopital's rule 5 times and I still didn't have an answer. So I said there's got to be a better way. And what we used to do before we knew L'Hopital's rule was we did this. Now I don't know if you remember doing that or not, but we multiplied numerator and denominator by 1 over 6 to the nth. Like that. That's what we used to do. That would be back in Calc 1. Do you remember ever doing something like that? It's effective when n is headed for infinity or minus infinity. Okay, you'll see the effectiveness in just a minute, but that's the reason I chose an example like this, so that if you have to do it, it's not totally out of the blue for you. Okay, now a real test of your algebra. What's 3 to the nth divided by 6 to the nth? You're right. Isn't it? Plus, what's this? 6 to the nth times 1 over 6 to the nth. Okay, what about denominator? Yeah, when you distribute that one, 1 over 3 to the nth plus, and then you do that one. Okay, now as n goes to infinity, where is 2 to the nth going? Well, 2 to the nth is going to infinity. 1 over 2 to the nth is 0. Okay. So you will agree that I can do that. And it's 1. Okay. So when I took the limit, I got 1. Now let's go back and interpret. I think I saved those. Here's the one I think I have right here. I took the limit of the ratio of these terms, right? And what did I get? I got 1, right? Which is bigger than 0. So what's the conclusion? Whatever one series does, the other one does? Well, the one I compared to, we said converged. So I can finish this by saying, therefore, by the limit comparison test, the series n running from 1 to infinity of 1 plus 2 to the nth over 1 plus 3 to the nth must also converge. So those are the comparison tests with examples to go with them. Does it make sense? So what's the downside of the comparison test? Trying to find a series to compare to. But as you look at it, there are hints. Okay? Okay, just one more. Page 709, number 24 out of the book. The series is n running from 1 to infinity of n squared minus 5n over n cubed plus n plus 1. I kind of just grabbed one more to see what you would choose for a comparison to this one. I want to see if I led you in the right direction or not. What kind of a series would you use for comparison here, and how would you know? Excellent. He says definitely a P series. What was the clue? Because they're in there. Whenever you have n to a power, think P series. Okay? If you ever have a number to a power n, then think geometric. I think we're going to get that across before test time, because that's kind of critical. Whenever you have n to a power, think P series. Whenever you have a number to a power of n, geometric series. Okay, now when you pick your P series, you should always pick the one that has what? Guess. I mean, I have n squared, I have n to the first, I have n cubed. What should I use for my comparison P series? N to the first, n squared, or n cubed? I always pick the highest power. Trying to get some principles down here so you have some idea. So I'm going to compare to the series n running from 1 to infinity of 1 over n cubed. I pick the highest power I see. Okay? And that one is known to what? Converge. Because P equals what? 3, which is greater than, okay? All right. The next argument would be, show that for n equal 1 to infinity, the terms stay positive. Well, they don't. That's part of the reason why I picked this one. Because if I pick n equal to 1, I get a negative number, right? Because it's going to be negative divided by positive. What if I picked n equal 2? Still negative. What if I pick n equals 3? Still negative. N equals 4. Maybe there's no hope for this. What about n equals 4? Still negative. What about n equals 5? What about 6? What about everything from 6 above? Okay, do you remember our famous theorem? It says when you check for convergence or divergence, it doesn't matter if you eliminate a finite number of terms from it. So, to satisfy conditions of comparison tests, we will investigate the series starting with n equals 6 to infinity. To keep terms positive. Okay? That's how we handle it. And then they say, but how do you know that if you go from 6 to infinity, the series from 1 to infinity is going to do the same thing? Well, we have a theorem that says delete a finite number of terms off from a series, it will not affect its convergence or divergence. Okay? So that's one reason why I picked this. The other reason was, how do you decide what to use for comparison? Okay, now I'm just going to check the limit again as n approaches infinity.
Teachers, please excuse these students to room 422 at this time. Katie Agius, Donald Buckley, Brett Friedman, Philip Hines, Desiree Corhorn, Tyler Melport, Nicholas Panic, Nate Roblin, Josh Tasman, Ben Villar, and Kevin Wright. They need to bring number 2 pencils and a calculator.
Okay, we're going to check the limit of my series compared to the one I know something about. Okay, this would be the same as taking the limit as n approaches infinity of n squared minus 5n over n cubed plus n plus 1 multiplied by n cubed over 1, right? Which is the same as taking the limit as n approaches infinity of what? N to the 6th minus 5n to the 4th over n cubed plus n plus 1. Okay? Now in the old days we used to multiply by 1 over n to the 6th, 1 over n to the 6th. You may or may not remember that.
Fifth. End of the fifth.
5.
You're up.
Yes. Thank you. That announcement got me rattled. So we get the limit as n approaches infinity of what? 1 minus 5 over n. And on the bottom we get 1 over n squared plus 1 over n to the 4th plus 1 over n to the 5th. And what happens? You end up with 1 over 0, which is equivalent to infinity, isn't it? Okay, now if we go back to our limit comparison test, and I think I still have a copy of that. Here it is. If the limit turns out to be infinity, and this series diverges, then what does yours do? Do you see a problem here? Of course, that's why I picked this. What did my known series do? And yet my limit came out infinity. So what's my conclusion? I can't make one. I can only make a conclusion like that if what? My original series that I compared to diverged. But now I am suspicious that my original series maybe wasn't convergent in the first place, right? And maybe my original series was a divergent one. So I won't have time to do this, but at this point you go back to there and you make up a p-series that diverges to compare it to. What would be the p-series that would diverge? 1 over n. So you go back and compare to the series 1 over n instead, which is known to diverge. Then you do the limit, and then it works out. So I want you to see, in this case, what can happen and how you deal with it. So if you pick a convergent series, which is natural, but you get this, too bad, you're done. Doesn't help. But then pick a series that diverges, compare it to that one. And then it does work out. And I don't have time to do that, but you can check that limit, right? And see what happens. Okay, we're out of time. Your assignment for next time is 11.4, obviously. You should have all the tools you need to be successful. But we won't see you again till Monday. So have a good weekend, and don't forget to do a little math here and there. And we'll be going over the assignment 11.4, and we'll go back to 11.3 to see if anything came up, because you're going to have enough time to look at some of the problems you didn't get to, maybe. I don't know. We'll see. Any questions?
No. Are you coming here tomorrow?
Well, what do you want me to do? I'm planning to, unless you don't want me.
We like you here.
Well, I don't know. If it's going to be helpful, I'll come. If you don't need me. What do you think? We got to decide quickly.
Yes.
Come?
No, it's not.
Yes, come.
Okay, I'll tell you what. I'm going to come, but your attendance is optional. So if you want to come and work some problems together, we will. If you say I'm fine, I won't make you come. Fair enough?
Okay.
So come if you want to. Even if nobody shows up, it's okay, because you're on my way to another destination. I mean, I'll feel bad, but I won't get upset. Okay, so tomorrow is optional attendance for Byron Center. Okay, I'll tell Mrs. Skierbeek that. Okay, see some of you tomorrow, perhaps the rest of you on Monday. Okay, calculus signing off.
That hurt.